So we are live. Here is this is our tentative schedule at the moment. We are right here at Friday doing rectangular waveguides on October 2nd. So we've just gotten through TE polarization. So we'll just do a quick lecture on the TM polarization for Monday. Then we'll jump into circular waveguides again. So you notice a bit of a theme here of just waveguides on top of more waveguides, and there's always going to be the TE and TM polarization for each case. And then there's the microstrip. So we could have done more stuff, like there's the coaxial waveguide, but I don't know if it's super instructive to just keep doing more geometries on top of geometries. So most classes tend to traditionally just do parallel plate, rectangular, and circular, just so you get kind of a nice feel for the mathematics of them all. And the microstrip is kind of this outlier because there's no like exact closed form solution to it. But there are nice sort of empirically derived approximations for characteristic impedance as a function of all the different parameters in it. So we'll do like a day just sort of discussing that. And you'll need this when we do lab number 4, which is going to be when we start making our own microstrip transmission lines. And then we'll just do sort of a review. And so tentatively, this is where it's scheduled here, depending on whether or not we get through all the material in time. But that's kind of the tentative plan, I think. That feels pretty solid to me as far as just going over all the waveguide stuff.
Sorry, Professor, are you
sharing? Oh, dang it, did I forget to share my screen again? You gotta tell me these things. Just let me babble for 5 minutes. So sorry, share. Sorry about that. I just did that twice today. 5 minutes ago, I was babbling at the mic and I had it muted without realizing it. All right, this is gonna be a rough day. I apologize. So this is just the tentative schedule I have here. Like I said, we are right here on, we're at Friday, October 2nd. So another week of more waveguide stuff, followed by the microstrip, and then an exam sometime around Friday the 16th. So that's, again, is just sort of tentative. I kind of just wing it depending on the flow of the material. Depending, like this stuff may or may not need an extra day or two, or maybe we'll get through it nice and easily, no troubles. So it's not set in stone, but that's kind of the tentative plan. And then we'll jump into all the wonderful world of microwave network theory. And this is about as far out as I've planned ahead. So a few weeks ahead in terms of planning our material here. So save that date, the 16th. Let's see. So everyone else is also here. I'm just going to do another quick screen share. Sorry. I was just telling everyone before class began that I've uploaded that little reference. We talked about how magnetic fields and H fields are sort of mixed matched a lot. So that is a paper I've uploaded that talks about the reason why they get confused and clears up a lot of the issues surrounding that. So that would actually make an interesting paper if you want to tackle that for your 6,000 level paper report. And I was going to say, if you find anything else interesting out there, I can upload them here as sort of academic sharing. There's no copyright issues with this sort of thing for sharing for a class. So if there's any papers out there that look interesting, we can stick them up here. So it's just in, you go to files, and then there's references here to look at that stuff. So be on the lookout for that sort of thing for your report. So let's, what else did I have? It's just short little announcements. So let's stop with the screen share. I've been thinking about doing sort of like a sticky point for the week kind of survey. This is something Dr. First likes to do in her classes a lot. And now that we've got a good groove going, this feels like a good feature to add because there's so much material just being blown at the students like a fire hose that I'm noticing, some little bits we're getting through the cracks, right? So there's going to be an idea here or there that I don't explain very well, or we cover too quickly, or I even had a typo in my notes on group velocity. I accidentally said beta over omega instead of beta over k kind of thing. So if there's any confusion along those lines, this will be a good way to get some of that stuff brought to my attention to review it again. So be on the lookout. I'm going to upload just like a little quick survey. It'll count as like, I guess, kind of attendance points kind of thing. And it'll just be, any suggestions, any stuff that was done well, any things that you thought were weak that we need to go over and reinforce by next week. Another thing I was thinking of is maybe like office hours kind of idea of, because there was a handful of students who were struggling to get some of the homework done because there were just a couple of those ideas that were not quite seeking in. So I was thinking something like on Wednesdays, either the hour after class would be a good time to just do homework questions specifically. So that way we can do lots of practice problems in class. And if you're genuinely stuck on the homework, this will be a good place to do that. Or maybe like Wednesday afternoon around 3-ish. So you will have had a good chance to do all the homework, but that'll be a good place to just meet up for an hour and ask very homework specific questions. Or just right here in lecture time is also a good time if there's anything that is really getting sticky. But it's thinking something like that, a little outside of the main lecture might be helpful. So let me know if that sounds appealing or if it's something you would attend periodically if I made that available. And then finally, there was some talk about creating a MATLAB code for the NanoVNA. So we have that NanoVNA saver, which is kind of, I mean, it works, but it is a little flimsy. So we're working on just a regular MATLAB code where you don't have to open up that saver anymore. You can just use MATLAB to connect to the thing and then just plot results and manipulate them immediately. Because that's what we're gonna have to do at the end of the day anyway, is import this stuff into MATLAB so that we can do some fun processing on it after the fact. So keep your eyes open for some nice MATLAB codes along those lines as well. I've even written a couple already, and so has the TA. So we can kind of go over that. Maybe next Monday will be a good time after I've had a chance to really get that stuff put together. All right, so if there are any other questions on that, we can kind of jump into today's material. Let's see, I should have published just sort of today's little in practice session. There we go. So on the Canvas page, here I'm going to share again. So there should be a sort of practice set of work we're going to go through today for October 2nd on the Canvas page. So again, this is just the sort of attendance quiz. So just follow along and turn something in that shows to prove that you were here and paying attention. So no time limit. I think it's due by 5 o'clock kind of thing. So if you watched the lecture, we got all the way up to where we derived this big nasty expression for the longitudinal magnetic field profile down a waveguide. And it's big and it's ugly, but it is tractable, and you can do a lot of interesting stuff with it. So all we're going to do now is work through the derivation for the other field components. So that will complete everything we need to know. And then I was thinking of walking through some MATLAB code to actually visualize this stuff, because it's one thing to see this big, horrible double summation of Fourier series on top of each other in 2 dimensions. It's another thing to actually create an image plot of it in some sense that visualizes what the heck those fields look like. Because the book gives you this very, very, very flimsy illustration of these modes. I'm going to turn to this. Yeah, this stuff back here. Let's see if I can find that page. So actually, I'm going to switch to my camera view. So we'll stop sharing. All right, so this is my desktop camera here. So these are the actual mode profiles that the book tries to give you. And this stuff you can see, I think this book is like easily 20 years old. So this would have been nice back in the 90s or early aughts before people were really good at visualizing these fields. So I've created some MATLAB codes to try and create a much better visualization of this stuff, because this to me just does not capture the essence of what you're looking at. But before you can plot that, you have to actually derive it. So where are we? So we have this solution that we derived, where the z component, the function of x comma y, is this double summation, n equals 0, m equals 0, and they both go up to infinity. And just incidentally, this is annoying to have to keep writing a lot. So what you might see sometimes is something that looks like the following. Oops. Sorry, get this cable out of the way. You might see something where it's just a summation over n comma m, like that. And this is just sort of a shorthand for that. So be mindful. I'm probably gonna have to start using this just because it saves time and ink. And I think sometimes it feels a little more instructive to say something like h sub n comma m, because these are h field amplitudes, or more generically, you can say a sub n comma n, just to keep in line with this idea of this Fourier coefficient here. But you got to be careful because there are multiple components, right? There's a z, x, and a y going on here, but they're all going to kind of depend on this coefficient anyway. So this is another one of those trials and tribulations, is when your math gets so complicated, you need to think of nice mathematical formalism to encapsulate it all in a nice, clean, intuitive way. So if you prefer one over the other, let me know. I'm going to stick with the A's, although I may sometimes default to the H here because it reminds you that it's a coefficient with units of amps per meter. So let me know if you prefer one over the other. At the moment, I'm kind of leaning towards the H, but I've been using the A's already. So let's just write this out. N comma m, A sub n m, and you have this cosine, cosine m pi x over a, and then there was a cosine of n pi y over b, e to the minus j beta nm, because there's an n and an m now, times z. So the geometry, just to remind ourselves, you have this rectangular plate of metal, looking something like this. And it kind of is that. There we go. So this is perfect electrical conductor on all sides. PEC, PEC, and then there's a PEC and everywhere, right? So that was our x direction. This is our y, and then z is kind of coming down the longitudinal direction. A little more light. So z hat. And so I believe x had a distance of a, and then this was b on your y. And whenever we're doing rectangular waveguides, it is usually, by default, we are assuming a is greater than b. Yeah. So hypothetically, b could be greater than a, but then you would just rearrange your coordinates to make that x and the other one y. So just by convention, it helps to remember a is greater than b. And so when we do these coefficients, you'll have a coefficient that's going to be A10, which represents the dominant mode. So that's just kind of reviewing some of the geometry of this stuff. And that is because this will have the lowest cutoff frequency due to this assumption of this being bigger than the other one. Okay, so otherwise, your A01 would be the dominant mode if you stretch it the other way. So it's just kind of a convention in our naming and our geometry here. And I guess you could put an equal sign there because they could hypothetically be the same length. Okay, so this is a big, nasty expression. So this is a double summation over these indices here. And each one of these is going to have this propagation constant associated with it. So I'm going to say beta sub nm. We're going to have k naught squared minus n pi over a, or sorry, is that m or n? I forget which one goes here. Where's my notes? Oh, nuts. I forgot to write that down. I'm going to assume it's, the n goes with the a. Oh, sorry. No, I believe it's m over a. There we go. And then n pi over d b. And then you have the square root. There we go. So you see how just tedious it is just to write down the basic equations. You have so much stuff you have to keep track of. But this should be pretty familiar, right? This is the intrinsic wave number. If I have some plane wave propagating in free space, it would have this wave number. But when you confine it to this waveguide, all this stuff starts interplaying with itself, because that same idea of these waves bouncing back and forth off the walls is still going to apply. But you notice, hypothetically, instead of just sort of going up and down, you can imagine in your head maybe a wave sort of bouncing sort of off the walls this way, right? So it could do this sort of weird corkscrew spiral pattern as it goes down the wave based on these two mode numbers rather than just the one. So it gets very, very difficult to visualize in multiple dimensions. So that's why I was kind of a big stickler for the parallel plate waveguide, to really visualize those ideas. Because once you add that extra dimension, it gets very difficult to picture in your head what all that stuff sort of represents. So as long as you can just imagine what it did for the basic case, just say it's the same idea with more dimensions getting tagged on top of it. So finally,
Forgot a square.
Oh, thank you. Square and square. Thank you. So this, just remember, this is technically that same Pythagorean relationship again. It's just if you have a sort of a triangle in 3 dimensions. So let's see if I can draw this real quick. This is a little nasty to visualize. So here is some coordinate axes like this. So here is x, y, and z. So kind of imagine the x coming out of the page. I'm going to just sort of imagine this is the hypotenuse of a triangle, like so. And then let's see if we can kind of, so this will be something like this. That makes sense. So you notice there's going to be, so that's the hypotenuse. I'm going to call that k, if it's like a wave vector here. And then we'll have, let's see, let's use a different color here. So you'll have this bit here and then this bit over there. So the way you would imagine that is, this is k sub x, this is k sub y, and then this is k sub z. So that idea of a Pythagorean theorem on a triangle still applies, because you can now write, k squared equals k sub x squared plus k sub y squared plus k sub z squared. But instead of calling them x and y and z, this z here is our beta squared, and then this is our m pi over a squared, and then this guy is our n pi over b squared. So in your mind, I just want you to remember this expression here sort of represents this sort of triangular thing. So I have a propagation constant coming in the z direction down my waveguide is my beta. And these are just these right triangle bits of it that are associated with it. So let's go back. So as what we're interested in now is, given this thing, can we solve for all of the other field components? Because we went through all of that hassle just to solve the z component of my h field, even though there's x and y for my e and my h, sort of blobbing, meshing all together down this waveguide. So the whole point of this formalism is, given this guy here, we found this solution, now we can derive all of the other bits. So what we found is h sub x is equal to negative j beta over k sub c squared. So there's this k sub c term also that the book really likes to use, which if I remember, where did I write that down? I think it was k naught squared minus beta squared. So we'll just make another little note over here, say. So k sub c squared was k naught squared minus beta squared, like that. So you have all these little annoying terms we have to keep track of. and partial h sub z with respect to x. And then we had h sub y was equal to negative j beta k sub c squared partial h sub z with respect to y. And then there was also, falling off the edge. And then there was e sub x, which was negative j omega mu naught over k sub c squared, partial h sub z with respect to y. And then there was the e sub y is equal to less j omega mu naught over k sub c squared, partial h sub z with respect to x. So all that yucky formalism we did pays off finally because we solved this. So now each of these guys is one little derivative away from getting a solution. And just FYI, this is in your book. It is back here on page, let's see if I can find it, right here, page 100 actually. So these are the terms that they derive here, if you like them nice and rendered out here, okay? So just remember that if you ever need it. So let's go ahead and do some derivatives. So welcome to the wonderful world of electromagnetics where you're just doing curls and derivatives on top of derivatives and just to get all of these field components figured out. So we'll start with h sub x is equal to a positive j beta over k sub c squared partial h sub z with respect to x. So this partial here with respect to x is the only thing you have to carry out. So I'm just gonna make a little note. So you start with this expression here and you just add a partial with respect to x and you're basically ready to go. So you notice this is a separable function here. So it's not as bad as it looks. This cosine term here will turn into a sine or a negative sine m pi x over a times the derivative of the inside, which will be m pi over a, like that. So this gets really annoying to have to keep writing. So I'm thinking it might make sense to default and just call this something like k sub x, x, and k sub y, y. But then you have to now keep track of the fact that there's an m and an n associated with it. So you have to write something like m or n, or you just remember in the back of your head that there's an m's and n's associated with this stuff. So you can see the notation just gets very cluttered very quickly. So we'll just see if we can't write this out explicitly. When in doubt, just write it out. J beta over k sub c squared. And then we will have a summation from n over n and m. There will be this a and m. And then you just have to copy all this out and you have to add these terms here. So I'm going to get a negative m pi over a. Negative m pi over a times sine, and now my hand is starting to cramp up. So I'm just going to say k sub x, x, cosine of k sub y, y, e to the minus j beta n m z, where just remember k sub x is m pi over a, and then k sub y is n pi over b. So I hope that's not getting too confusing, but it's the only way to just make all this stuff fit onto a single sheet of paper at this point, is you have to start smushing this into a smaller variables. But there you go. That is basically our answer. And sorry, this is a little flub the book kind of does. You notice it just says h sub x equals this minus j beta thing here. But technically, this is a summation. This is a double summation over all of your m and your n. So that beta and that k can't really be outside of the summation. This is only true for one of the terms in the summation, which means you got to be a little careful. This guy here, this term, technically needs to be inside your summation in order for that to work. So what we can do is just a little bit of chalkboard magic, where I'm just going to cross that out and put this over here like that. So don't make that mistake. Remember that the equations in the book only represent a single one of these terms in this summation, this possible summation. So they only give you sort of the generic solution, but they don't emphasize the fact that each one of these solutions added with another solution is also a solution. And inside of this waveguide, you could have some infinite superposition of all these modes just blending together, blasting down the waveguide, which is what happens anytime you try and excite it with something. You get that kind of modal excitation over all of those amplitudes.
Is the book wrong because you put a positive J beta and the book has a negative?
Oh, pardon me. That would have been my mistake here. I had negative here when I wrote this down. I just put a positive. I read the wrong term, it looks like. So sorry, thank you for catching that. And those negative signs are going to bite you a lot if you're not careful. So thank you for catching that. That was a negative. Okay, so that's the answer for your hx. So let's just write this out neatly now. Hx is a function of x comma y is equal to summation over n and m. And then we're going to get an a sub n m. And you'll notice these two negatives are going to cancel out on each other. So I will get j beta sub n m times m pi over a k sub c squared, like that. Did I miss anything? Yeah, that looks about right. And sine of m pi over a times x cosine n pi y over b, then e to the minus j beta n m z. There it is. So it's big and it's yucky and it's horrible, but you can kind of see in your mind, each term is representing something very specific. This is the sort of the excitation mode amplitude. This is just the thing that came out of the derivative to go from the z component to the x. These are the sort of mode solutions that were imposed by the boundary conditions. And then this represents the propagation down z. So it's important in your mind to not just blindly crunch out a bunch of symbols, but to sort of ask yourself, remind yourself, what does all of this stuff kind of represent at the end of the day? So there you go. So you can see it's not too bad. It's just some derivatives, but it's just there's so much stuff that you have to keep track of and copying and pasting that it's very easy to mistake or make little, forget little bits here. And then if nothing else, your hand's going to get very cramped up very quickly if you aren't careful. So h sub y now is this guy here, negative j beta over k sub c squared. So we're going to do the same thing on the y derivative here instead of the x. So you can see there's some parallelism. I only have to change one little thing. This guy is going to be a cosine. This one's going to turn into a sine. And this term here, instead of being m pi over a, is going to be the n pi over d. So you can just sort of jump right to the end now. So it looks awful, but really each of these steps is relatively straightforward. So you get a sub n m. And then we'll get the same sign up in here. So j beta n m n pi over b k sub c squared cosine m pi x over a. And then this guy will become sine n pi y over b e to the minus j beta n m z. Like so. And then as an extra dummy check, these are also in the book. We have the rectangular waveguides. They go through this same thing. So here we are. Oh, did they not give? Here they are. Sorry, here we are. So, okay, there's your, oop, let's get that up in the camera view. You see that? There we go. So these are the solutions here. You see how they fell out pretty neatly. So j beta m, j beta n. So you get sine cosine versus cosine sine, and then we'll go ahead and repeat for the other two. So E sub x. So now it's going to be a little bit different. This is what we got here. Negative j omega mu naught. So this is going to change the units from amps per meter to volts per meter, or k sub c squared partial h z with respect to y. So this is technically, you know, for a given n comma n here. So remember, there's a summation kind of implied here with the way the book has done it. So we'll go ahead and just carry that out. We'll have our double summation, just n comma m. The a sub n m is going to translate through, and then we're going to get a negative j omega mu naught. This can actually go out front if you want, for k sub c squared. And again, remember, this k sub c also changes with n and m. It's just not explicit. And then that derivative on y is going to act on this term here. So then we're going to get the same n pi over b with a negative. Then we'll have basically just cosine sine again, e to the minus j beta n m. You just, it's you get kind of sick of writing this stuff out after a while. So then, yeah, plus and plus, and then you're good to go. So does that match? So we got e sub x, we got a j, the j omega mu naught, n pi over b with our kc, and you see cosine sine here, e to the minus j beta z. So you can clean that up. It's just some coefficients here. And of course, you know, there's some stuff buried into those arguments. And then finally, our y component on our electric field plus j omega mu naught over k sub c squared partial h sub z with respect to x. So that should be fairly straightforward. So summation n comma m. I'm getting a little flimsy with my notation now. So a sub n m, that's going to translate down. And we're going to just get m pi over a. So let's see if we can lump all of that together now. J omega mu naught negative m pi over a k sub c squared. Did I miss anything? I think I got all the right terms in there. And finally, cosine, sine. Oh, crap, sorry. Sine, cosine, excuse me. I was hopping over too much. I meant to do the partial on x, means sine, cosine. So m pi x over a, n pi y over b, e to the minus j beta m z. Ugh, there we go. So you can kind of feel the mathematical fatigue setting in as you go through all that. But the good news is, at the end of the day, you can just dump this into MATLAB. And again, MATLAB will crunch on this very, very happily, provided you don't accidentally mismatch the occasional minus sign or coefficient in there. So that's the tricky part into the end of the day. So the long story short is, given this guy here, which we solved, all of these other terms fell out just doing some basic calculus and derivative. So we can take all of that and dump it right into MATLAB and see what happens, which coincidentally I have already done. So I'm thinking, as a homework assignment, I may want you to try and create some image plots, because this is a good skill to have, is we've done a lot of visualization with just graphs in MATLAB. So what would it take to create a two-dimensional sort of cross-sectional visualization of this thing? So let's go ahead and screen share. So I've got a code here. So I've put together kind of a demo code that will do transverse electric rectangular waveguide. So you can actually just define a bunch of mode amplitudes. So let's start with, say, the 0, 1 mode, like this. You notice I'm giving it an amplitude that is imaginary times 1. Furthermore, the 0, 0 mode is nothing. That will have no propagation in that. And we also have to be careful. MATLAB is 1 based and not 0 based. So when you define like a matrix of mode amplitudes, your 1, 1 entry is actually the 0, 0 mode. And then 1, 2 is 0, 1. So that means 2, 1 would actually be my 1, 0. So let's do that. So there's a whole lot of annoying little things you got to be careful of there. So just remember, you got to subtract 1 from these indices to get the actual mode numbers out of this here. So I kind of put a little note here to remind myself which one corresponds to which. So, and then you notice I'm doing an imaginary because the electric fields already have an imaginary value to it. So if I have a real valued constant on my H field, there will be a J on my E field, meaning it's going to be 90 degrees out of phase. So if you want to sort of create a real valued plot, you have to just give it a sort of a phase shift with that J is all. So I'm going to go ahead and hit that. And that is what you'll see for the 1, 0 mode. That's the dominant mode in a waveguide. So you see it's 1.5 meters by 1 meter here. And you see the electric field only has a Y component because the X1 went to 0. Yeah. If I do 1, 0, am I doing that right? Yeah. I may have a little, I believe that I put in the code here. Yeah, so I should just see the Y. Yes, that's right. So the 1 and 0, yes. Sorry, you got to remember because there's a sine and a cosine being multiplied together. So the 0, 1 is corresponding to the sine term on the E sub x, which is making x go to 0. So there's no x pointing to these vectors. They're all just y. And you see they go from 0 to a peak to 0 again. So what I can then do now, let's do, say, the 2, 0 mode. So we'll say 1J, like that. All the others are 0. And you see it just adds this sort of thing. So you see it goes up and then down, like so. And then we can, of course, make the 3, 0, where you'll probably see up, down, up, or maybe down, up, down, depending on the signs here. So let's go ahead and say 4, 1. So that's going to correspond to 3, 0. So you see up, down, up in the vectors. So now we can also do the same thing on the X component of my electric field. So let's look at those. So those were the dominant modes. Let's do 0, 1 now. So you should see the same thing. It's just going to now point along a different direction, like so. In this case, because of our phase shift, it's going from right to left. So remember, we're looking down the cross section of this waveguide, and this blob of energy is like hitting you in the face, right? Sort of like a kind of like getting blown in by a fan or a wind, right? There's this invisible energy bouncing around inside the walls of the waveguide, and you have all of these fields, electric and magnetic, and we are just looking at the electric fields right now because they don't have any Z component here. They are propagating in Z, but they will not point in Z, if that makes sense. So then, of course, we'll do the next one. So let's do the next mode. So let's go to, let's see, that was 1, 2. So I need a 1, 3. Let's do that guy. That'll be 0, 2. 1J. There you go. So you see that same thing where the electric field is doing these sort of up-down patterns. You notice the tangential component is 0, but the normal component is not. So that implies there's actually a little blob of positive charge kind of collecting on your metal plate here, and then a little blob of negative charge over here, and then vice versa on the other end of your waveguide. So there's a little surface charge density on the walls of this thing. So now let's get a little more interesting, and we're going to do, say, the 2,2 mode. Okay, so 2,2. And you see this sort of weirdness now. So you can kind of see it gets a little wacky to visualize in your head. So these are both dominant modes superimposing on each other at the same time. And you can see that the field profile is getting a little wacky, right? So we see now there's charge on all sides of the waveguide here. And if you sort of count the peaks and valleys, oh golly, it starts getting very confusing very quickly when you start doing that. So let's go ahead. Oh yeah.
Yeah. So when you said that there's a surface charge accumulating on the surface of this waveguide, that means this thing's going to heat up based on how much power is going down it.
Technically, yes, but this is a perfect electrical conductor in this situation here. So a real conductor will be very, very close to this. But if there's some finite conductivity, then that means this charge is not perfectly concentrated on the surface, but it'll actually penetrate into the conductor a tiny bit. And it can lead to heating, ohmic loss, in the walls of the waveguide. And you can hypothetically solve this all exactly and account for that penetration into the walls as well. But you can see how mathematically this was just intense enough. So when you start adding those extra little layers of field components to solve for, it gets very nasty very quickly. But yes, in your mind, you can imagine there will actually be these little charges and currents are getting sucked into here as well, because this whole thing is like propagating down the waveguide. So this charge is in kind of a motion. So there will be currents squishing together here. Yeah?
Yeah, this is just from an observation, because I've noted once you start moving into high power systems, they start using waveguides versus some type of microstrip system. And I was thinking maybe the waveguides are just, there's less ohmic loss, so there's less heating involved in it versus the microstrip that we see a lot of.
Yes.
I don't know.
That is very accurate, because most of the power, the energy in this blob of this wave going down the waveguide is contained within these fields. And if it's just filled with air, there's nothing to ohmically dissipate energy. The only loss you'll get is that tiny little bit of field penetration into the walls of this thing. And if it's made out of copper or something, which is extremely conductive, that energy loss is very, very minimal. So you can easily blast like hundreds of kilowatts of energy in something like this, which is, so my understanding is this is what you would do in like a radar system, where you need like little short bursts of megawatts of power to start tracking things far away. And so, yeah, you would not want to send that down like a coaxial cable or something. You would need something like this to carry that level of energy. But yeah, all the energy, most of the energy is contained in these fields, and the greater the conductivity on the walls, the less that energy actually gets into the walls to heat them up. So this is definitely a very efficient way to send huge amounts of power in the form of an electromagnetic field in a nice concentrated volume here. So let's go ahead and look at 2, let's see, that was 2, 2. Let's do 3, 2, like that. So you see this sort of, so you can see that the structure is getting very complicated, but you get that sort of same periodic essence to it, where you can sort of count the peaks and valleys as you go higher in mode number. And it's just these sines and cosines sort of adding up on top of each other in the electric field. And we could go through and do the same thing with the magnetic fields, and you just see some blob of energy with these peaks and valleys associated with it. So let's do a couple more just for fun. Let's do like 4, 2 maybe. So you'll see something like that. So you can see that there is a certain pattern here of just these repeating cosines overlapping on top of each other. So right now the color here is representing the intensity of the electric field independent of its direction. So the length of the vector here corresponds to the color. And depending on the length of the vector, so you see there's no actual vector here. So that's the trough here. So blue means weak field, red means intense, and then the vector is just sort of telling you the direction of that field. Then we'll do something like 4, 3, and you'll see this sort of wackiness going on, right? And eventually you'll get to cutoff. So that's another very important thing to remember. All that idea of these wave vectors adding up to give you real propagation versus imaginary, it's still in the math there. So as I keep going up and up, eventually you'll get to a cutoff. What's also important to remember is this idea of, if I tell you the field profile, I can put in any arbitrary scalar field I want along this cross section, and that same notion of mode orthogonality will apply. We're not necessarily going to do it in this class because it would involve all these horrible two-dimensional Fourier transform things, but you saw how it gave pretty neat results to give you the mode coefficients when you did that. And that same rule will apply when you go into 2 dimensions. Okay, so that is a nice fun visualization here. And I'm thinking probably next Monday or so, we'll put together a crude code just to show how you can create some of these plots yourself maybe, or unless you're just kind of happy looking at this here. I was thinking it'll be instructive to kind of have your own little code that does this, so you can kind of play around with some of the field profiles for your own enjoyment. Because this stuff is just nasty enough mathematically that it's nice to be able to tie a picture to it at some point. Because again, just to remind you, I'm going to stop sharing real quick. Let's go back. So here's what the textbook, so compare that to what the textbook drew here. So you can definitely see that those nice full color renders convey a lot more information than what you get out of here. So what I did was just the cross section here. So we were looking, so here's the waveguide. You see it does 3 cross sections. So I was just doing the 3rd cross section. You could see how it had that same field profile. And then you start seeing these different blobs of energy as you go. I'm also not even sure what the heck they're plotting here, because it just says field lines. It doesn't say whether you're looking at the electric field or magnetic field. So I think that was kind of a big oversight in the book here. You see also it says reprinted from some other book from 1965. So these images were originally rendered in the 60s. So somebody desperately needs to upgrade their visualization at some point. I think I should write them a letter maybe and say, hey, do you want to fix those images a bit? Because this hasn't been touched in like the last 50 years apparently. So there you go. So that's why I think that the MATLAB stuff is very instructive, because it's very hard to see this sort of stuff in a modern textbook. Okay, but there we go. That's all I have for today. So I will open the floor to any questions if there's anything you want to talk about. Otherwise, I'll quit the recording.
I just wanted to apologize to have you go back and revisit. Could you go back to the simplest case where you started at mode, I think it was 0, 1?
Yeah.
I think, just for me at least, diving straight into mode 4, 1 or whatnot kind of confused me.
Actually, let's do 1, 0, because that's traditionally the dominant mode. There you go. So this is the one that should have the lowest cutoff associated with it.
And don't forget to share your screen as well.
Oh, thank you. Sorry. There you go. So there's the, that is the 1, 0 mode.
1, 0 mode, okay. Now, you pointed out, I was just busy looking back at the equation. You mentioned that, so 1, 0 mode, this is the electric field. So we are looking at the EX equation that we derived. So cosine of, you said one of these turns into 0, one of these turns into 1.
Yeah, so so let's stop the screen share and we'll go back to the camera here. So these are the big equations. So what you saw was, what did we do? We did m equals 1 and n equals 0 is what you were just looking at. So the 1, 0. So if I put in a 0 for n, then that means this term here, this sine term went to 0, which means this whole EX term went to 0 as well. So this
EY
Ly
is the only one
disappeared.
that
And all you're
exists.
left with is Y. So then I put a 0 in for here, this cosine goes to 1, and this becomes a sine pi x over a. So let's just make a note. So what'll happen, this will imply EX equals 0, because this sine term zeroes out everything in the entire series. Well, I guess there's only one term in the series, I should say. So it zeroed out everything in that term. And then we get EY is going to be a single term where we're just going to get some coefficient times sine of pi x over a, like that. And we're looking at a cross section at z equals 0, so this guy is also not doing anything. So this is basically all you're seeing for the 1-0 mode. You get a sine of pi x over a. And it's going to be constant across all values of y, right? So there is no change in y. Partial with respect to y is 0, because this is a function of both x and y. So if we go back now, I'm going to share my screen again. You see there is only a y component. It is not changing in y, and it just goes, it's a sine function like we saw before. So it starts at 0, goes to a peak, and then goes back to 0 again when you hit the other end. So,
Why is there, I apologize.
no, fine, it's okay.
The arrow vector direction is propagating. So we're looking into Z, or we're looking where Z is coming out toward us, right?
Yes.
And I guess I'm confused. The arrow, so it's going up and diminishing. So we're just seeing like half of a sine wave here, correct?
Yep, that's correct.
Okay. So half of a sine wave, it goes up and down. Are the arrows and the colors denoting the same thing?
The color denotes the length of the arrow, the intensity, but not its direction. So the arrow is changing in length and direction, and the color is corresponding to its length.
I see. Okay. So if we went to mode 2, I think it was that where this split into 2 directions, right?
So it's not that it's split in direction per se, but I know what you mean. You get the 2 blobs instead of 2 peaks, right? So it's also important to remember that this is just a cross section. This thing is propagating down this waveguide. So it's like if you shoved your face inside of an air duct, I guess this rectangular duct, this would be the electric field blasting you in the face as it propagates down the waveguide. So you could look at multiple cross sections and kind of get a sense of how it's propagating. But you have that longitudinal propagation where it'll be kind of sinusoidally oscillating in your face and down along Z as well.
So this is a picture of us getting blasted in the face with a full period sine wave from 0 to 2 pi, right?
Yep, that's exactly it.
Okay, all right. And y is still not a, there's no sorry.
There's no change along y, that's correct.
No DE, no ED. I don't know what I'm talking about.
There's no derivative along y still, because that 0 on the other term has prevented that.
All right, thank you for going through that.
And I understand it's totally sort of mind bendy to go from all that horrible math to try and visualize it, but so it's okay if it takes a few tries to sink in, because this is not intuitive stuff. So another fun thing, you can just arbitrarily add modes together. So I'm going to just say add this one plus, I don't know, this one over here. I have no idea what this will look like, but you'll get a superposition of, and you get this sort of weird blob of energy now, right?
And just to make sure I'm getting this right, so as we go up in nth order modes. So we get more and more modes, the
Mhm.
frequency cutoff goes down. So we're reducing the usable frequency bandwidth of our waveguide by
Yes.
having more modes.
Uh-huh.
And so that's why this is of interest to us. Less modes, more frequency, or we could use this as a filter or something.
Well, that's one of those things where, you know, the expression one man's signals, another man's noise. Depending on your application, this cutoff stuff may or may not be a good thing or something desirable. So in some cases, it'll be something you can exploit. In other cases, it's something you're fighting against, right? Because bigger waveguides allow more modes of propagation, but bigger is not necessarily better because you want to shrink stuff down as small as you can get. So there's a lot of trade-offs in terms of the physics here, what you can and can't do or what you may want to do.
I also have a question about the, so you were setting the other modes to 0, but you were setting the single mode to 1i or 1j, so imaginary amplitude 1, positive imaginary amplitude 1.
Yes.
Right? And this is the single, this is kind of, to use an analogy from the, so we're going into 2D, going back to 1D now. This is not the summation of previous modes superimposed on top of this. This is just the individual mode being plotted, right?
Yeah, right now this is an individual mode. And then over here, I just started adding them together. And that would be what multiple modes smushed together might look like. So that was 1, 0 and 1, 1 superimposed on top of each other now.
I see, okay.
So you can get sort of weird patterns as you just arbitrarily add more information on top of these things. Because it's that same thing. Any scalar field you can imagine can be broken down as a linear superposition or some linear combination of all these modes. And that was just as true in 1 dimension as it is in 2 dimensions. So when you just start adding them together, you get just some weird scalar profile. Yeah, so somebody could ask something.
Yeah, and that's what they do in optics, correct? Because I remember hearing something that the amount of information that they could move over a fiber optic cable went up by orders of magnitude, because they figured out a way to shove multiple different modes on the same cable and then pull those modes apart or something of that nature.
I don't know if that has been done. I know in theory it could be done. I don't know if that's been done in practice, because when I took integrated photonics, the problem with that is getting the information out of each individual mode can be difficult, and they'll propagate at all different velocities. So I'd be very impressed if someone figured out a way to do that, because in principle, you sort of can. What you would need is some way to unpack those modes after the fact without all of them interfering with each other at your detector. But I know, like, in principle, that is possible. If you use each little mode and modulate it a little bit differently, you can send information down as if it were sort of a different transmission line. But I remember when I took integrated photonics, the general consensus, but that was like 10 years ago, is that multimode is generally bad because it causes dispersion, unless you can find a way to separate them somehow with the detector. So I would genuinely be interested to see if someone has done that by now. I know I've heard people trying to do that. I just don't know how successful it is. But I was just going to make one other little note. You notice how the electric field has this J term here? So if I have just a real value up here on my HZ, then my E field will be 90 degrees out of phase, which means I will get an imaginary only on my electric field profile if I put in a real value for this A. So that's why I'm adding another J on that term, because I'm plotting the real of this at the end of the day. So we'll go back to screen sharing. So when you see my little mode amplitudes, I'm just adding a J term so I get a real value when we do the plot. Otherwise, it'll be 90 degrees out of phase and everything will be 0 between your E and your H. So you have that sort of extra layer of weirdness on top of it, where the bits where your magnetic field kind of goes to 0, you'll have a max in your electric field and vice versa because of these relative phase shifts between all these field components. So it's
instead of,
yeah.
So instead of calling the real function call on MATLAB when you're computing this stuff, you're just snaking in this extra I where it's not supposed to be analytically in the formula that gives you the desired results?
Oh, it can analytically be in the formula. So here, we'll go back here. You can think of it in terms of this coefficient here is a complex number. It can be real or imaginary. And all that would represent is some phase shift on my signal here. So you start here on your Z component of your H. That number can be real or imaginary. If it is real, however, and you go back here and you see it will become imaginary on my electric field because of that J. But if this is already imaginary, then the J's cancel out to give me a real again. Is that kind of what you're asking? But yeah, this can be complex, this coefficient here. All it would represent is some relative phase shift along Z.
But that term only goes into complex when we're looking at evanescent waves. So we're past cutoff at that point.
Oh, okay. So cutoff. So let's go back again. Evanescent has only matters on this term over here, this propagation along Z. So if this guy becomes imaginary, then that is when you have an evanescent mode and you're in cutoff. So my amplitude can be complex and it will represent a phase shift. But if my propagation constant is complex, it will represent an evanescent or decaying mode. So don't confuse these two, the meaning behind these two coefficients here. So that's actually a good point, is that idea of cutoff. You notice this is the expression here for my propagation constant. And if my mode numbers get high enough, either M or N, or both, I eventually get that same problem where this becomes the square root of a negative number, and this guy becomes imaginary. It will have a J on top of it, which you then look onto this term up here. The J times the J gives me a real value, and I get an exponential decay or growth. So that's a long train of thought to follow, but I hope you were able to keep up with that. It's okay if it takes a little bit to sink in. Okay, anything else? And just remember, K sub C here is just a shorthand for this little term here. So the book calls it your cutoff mode number, which I'm not entirely sure I like as a name, but that's that. But this little term happens so often that they just gave it its own little name, K sub C. So that's another very important little coefficient to remember. So we got a lot of equations, a lot of math, and we'll put together some homework problems that really try to reinforce and practice a lot of this. I would like to maybe do a sort of an in-class thing where we kind of code up a visualization of this together, because it would be interesting to have your own MATLAB code that draws this stuff. It's pretty straightforward. You don't have to come up with all the stuff yourself. We would just kind of code it up together, or I can make it available just on Canvas where you can see this stuff in action. But it'd be nice to be able to pick cross sections as well. Sorry, go ahead.
No, I would just want to say I'd very much like that, either in class, a homework assignment, or just give us the code.
Yeah.
So we can play.
I'm thinking we'll make it like a homework problem to do that, but then we'll just kind of do it all in class. So everyone has that code and you can play around with the visualization of this. Because you've already done like the same thing in one dimension. It's just a few minor changes in MATLAB to get the full 2-dimension. The tricky part, however, will be these vector fields. If we go back here, I'm going to share my screen. The arrows here, that is a special code I kind of made myself a long time ago, which I can share. It's just, it's a little tricky to use. So if you're comfortable with that too, I can make that available. You can play around with and see these field profiles for yourself.
You mentioned orthogonality in passing through the different modes. I think I missed what exactly you were speaking to when you mentioned that. When did that come up?
So remember in the parallel plate waveguide. So let's go back to just a blank sheet here. So you had that problem where I could give you a field profile. I would say something like E of x of y comma z would be a summation of a sub n, I think it was it sine of gamma sub n y. I can't remember off the top of my head. Was that a sine or a cosine? I think it was a sine. E to minus j beta sub n.
I think it was a sine, yes.
Yeah. And so the idea was I could give you, we would say something like let z equals 0. So I'm looking at just like a little slice down the waveguide. And you would just have this Fourier series here. It would be a summation of a sub n sine of gamma sub n y was equal to some function of y. So some slice down my parallel plate waveguide. And we did a fun little derivation where we found that if you were given this information, you could calculate these using a simple formula where your a sub n was the integral of 2 over d, the integral from 0 to d, f of y, sine of gamma sub n y dy. So that you could use to reconstruct your coefficients. And the key to this insight was the notion that the integral from 0 to d of sine gamma sub n y, sine of gamma sub m y dy was equal to 2 over d delta mn. So it was 0 for everything except n equals n. So this idea here is the notion of orthogonality, which you can think of, it's like perpendicular, but in a much more abstract sense, where you can think of this as sort of like a dot product between two vectors, only they're not really vectors in space in the traditional sense. They're vectors in the sense of an abstract vector space. And this has the properties of an inner product. So if you remember way back when you took linear algebra, you probably discussed some of these ideas. But that is orthogonality in a nutshell, is it has all the properties of an inner product.
I see. So that what you've circled there is the reverse, the solution to the reverse problem, where we're given the E field and then we have to work back the coefficients that multiply each.
So this here is the solution to the inverse problem, but this property of orthogonality was essential to deriving it. Does that make sense?
Oh, I see. So this was not the rectangular waveguide's reverse derivation of AN.
No, this is only for the parallel plate waveguide. What I was trying to say is you could do a similar derivation in 2 dimensions for the rectangular waveguide, and you would have a similar orthogonality relation, but it would be much bigger and nastier. It would involve doing orthogonality. I think you would get like a double integral here from, say, 0. You get something like 0 to a and 0 to b, and then you'd have, you know, your cosine and then sine. So I've never done that particular step before, but if it applies here, it should also apply in the multiple dimensions. So you'd have like your cosine with a sine kind of thing happening, and you'd eventually end up with some kind of delta at the end. But now you have an n and an m to keep track of when they're multiplying together. So you need a bunch of indices here, probably n, m, k, l. I don't know for sure. Again, I haven't actually done the calculation. I know something similar, however, will apply when you do this double integral over these sines and cosines.
All right, thank you. I think there was something you pointed out while you were pointing to the heat map, and I missed it in passing, but okay. I think I understand orthogonality. I just was wondering how it related to what we were looking at on the heat map.
So that same idea applies, is I can give you some arbitrary field profile here for my H sub z, and you can break it down as a superposition of various modes. And those modes will span the space of all continuous functions within this region. And it'll still have that same Fourier series effect. You just imagine it going along 2 dimensions instead of 1. And it's mind warpy. And it would be fun to kind of do that someday, because I imagine you could do a lot of fun engineering design with rectangular waveguides if you could write a code that breaks all this stuff down. But that's there. Like the math is there, and people have probably done it out there in the world somewhere. It's just this is now getting to the point where it's just way beyond what an undergraduate should be expected to do, because there's so much other stuff we want to cover eventually. So they kind of leave it as you saw it for the one-dimensional sort of case. Now just in your mind, pretend the same thing is happening in 2 dimensions, even if we're not going to take the time to solve it and calculate it. But you notice, again, I can just start adding modes up together. So let's just add U on top of, I don't know, U. What will happen is you get some, wow, that did not, oh, I think, oh, that's right. It's not quite the same now, because different modes are going to dominate relative to other modes if you're not careful. So you can't just, you can add them together, but it won't look as interesting if you don't normalize their intensities. So here, let me stop sharing again. So that's why it doesn't look like as much is happening. Because you'll notice I can set this coefficient here, but it's going to be scaled by this m pi stuff over here. And this propagation constant is also going to scale its relative intensity. So yes, you can arbitrarily add them together, but certain modes will dominate others because their relative scale is going to be changed by these little coefficients here. So you got to be a little mindful of that. So I guess I could probably add my 3, 2 with like my 2, 3 or something if they're roughly the same scale. I'm not sure. But yeah, that like you can add them together. Let me share again. There you go. So I ran that. So you can see stuff like that happening. But if you start adding like the first mode with the 5th mode, they're not going to be in the same scale necessarily if you aren't careful, for the electric fields at least. But you can see just adding a bunch of modes together, you can start getting these weird wibbly, wibbly wobbly fields going there in those profiles.
Personally, so just asking your perspective, as you, a postgraduate, PhD program, do you tend to not believe hand-wavy explanations until you prove it mathematically for yourself, or is that expected of a grad student?
To prove stuff yourself?
To prove it to yourself in rigorous mathematical derivation. Otherwise, you don't really believe what you're seeing, I guess.
Me personally, I prefer to really ascribe the math to this stuff, because a lot of those hand-wavy explanations will turn out to not be entirely accurate if you're not careful. Or they'll have a bunch of asterisks associated with them that you're not aware of because the assumptions weren't explicitly stated.
So for instance, it seems like we